NOAA just issued a G2 geomagnetic storm warning. Solar wind racing toward Earth at 700 kilometers per second. That alone would be worth talking about. But that's not why we're here. Because while the news is covering the storm warning, almost nobody is talking about what's happening on the far side of the sun. Over the last 72 hours, 3 massive explosions erupted from a region we can't even see directly. It's hiding just behind the solar horizon, rotating slowly toward us. And there's one question nobody has answered yet. How powerful is this thing when it finally faces Earth? That's what we're going to find out. And the answer involves a 9-hour blackout that hit 6 million people with 90 seconds of warning. But first, what's hitting us right now? Tonight, Earth's magnetic field is being rattled by a coronal hole, a wound in the sun's atmosphere where magnetic field lines don't loop back. They open wide, like an exhaust vent, letting solar wind escape at extreme speed. Normally, solar wind travels at about 400 kilometers per second. The stream heading for us? 600 to 700. NOAA expects impact late April 17th, persisting through April 18th. They've classified it as G2 moderate on the 5-point scale. What does G2 mean for you? At high latitudes, power grids may trigger voltage alarms, geomagnetically induced currents flowing through lines the grid was never designed to carry. At G2, operators monitor. At G3 or above, they start deliberately cutting power to some areas to prevent cascade failures. Satellites feel it too. The atmosphere puffs up during storms, increasing drag on anything in low orbit. Operators may need to fire thrusters to correct orbits. Your GPS might drift, not dramatically, meters, not miles, but for precision applications like agriculture and aviation approaches, it matters. And for aurora chasers, the northern lights may be visible far south of where they usually appear this weekend. But here's what makes tonight's storm a footnote. This G2 event comes from a coronal hole, recurring, predictable, manageable. Grid operators deal with them routinely. What's happening on the far side of the sun is none of those things. April 13th, the GOES-19 satellite captured a dramatic eruption over the southwestern solar horizon. No flare activity was visible on the Earth-facing disk, confirming the blast originated from the far side. The resulting coronal mass ejection wasn't aimed at Earth, it was aimed at Mars. April 14th, a second eruption from the same area, same southwestern horizon, same pattern, massive blast, invisible from our side. 2 explosions in 2 days from the same location is not a coincidence. Something extremely active is hiding just beyond what we can see. April 15th, a third eruption, but this time from a different location, the northeast side of the sun. Soho's LASCO C2 coronagraph caught it. NOAA described the resulting CME as a partial halo event. 3 blasts, 3 days, 2 different far-side locations, all invisible to anyone only watching the Earth-facing sun. Here's why this pattern should concern you. The sun rotates once every 27 days. Whatever produced those southwestern eruptions is slowly rotating toward us. Depending on its exact position, it could face Earth within 5 to 10 days, and when it does, any eruption it produces will be aimed directly at our planet. We don't have direct images of this region yet, but we have clues. The CME from April 13th will reach Mars by April 18th, powerful enough to cross interplanetary space to another planet. Far-side events are usually invisible from Earth. The only reason we detected these is because the eruptions were massive enough to send material above the solar horizon into our coronagraph's field of view. Scientists noted that what we observed likely represents only a fraction of the true scale. And 3 eruptions in 3 days from the same region typically indicates a large, complex sunspot group with deeply tangled magnetic fields. The exact configuration that produces the most dangerous storms. Now here's where the history becomes personal. March 13th, 1989, Quebec, Canada. A massive CME struck Earth's magnetosphere. Within 90 seconds, the entire Hydro-Quebec power grid collapsed. 6 million people lost electricity in the middle of winter. Transformers overloaded. Protective relays tripped in sequence, cascading across the province like dominoes. The blackout lasted 9 hours, schools closed, traffic lights went dark, hospitals switched to generators, and it started with something that looked a lot like what we're watching now. An active region flaring repeatedly before launching the CME that made it to Earth. That was a G5, the maximum level, And in 1989, the grid was simpler and less interconnected than it is today. Today, longer transmission lines mean more surface area to pick up induced currents. Those currents physically damage transformers. And extra high voltage transformers, the backbone of the grid, are custom built. Replacing one takes 12 to 18 months. There is no strategic reserve. A Lloyd's of London study estimated a Carrington-scale event could cost the US alone up to $2.6 trillion. And in July 2012, a Carrington-class superstorm missed Earth by 9 days of orbital rotation. The National Academy of Sciences estimated recovery time if it had hit 4 to 10 years. 9 days? That's the margin between a near miss and a civilization-level event. Let's be clear. Tonight's G2 storm won't cause a blackout. It won't fry your GPS. It might give you a beautiful aurora display. The reason we're talking about Quebec and Carrington isn't because of today. It's because of what could happen in 10 days. So what do we watch for? NOAA's Space Weather Prediction Center will issue new forecasts the moment the hidden region becomes visible. If the sunspot group is magnetically complex, classified as beta, gamma, delta, that's the red flag. Those classifications have preceded almost every major geomagnetic storm in the modern era. If it produces an X-class flare while facing Earth, higher-level watches will follow within hours. And if a full halo CME is detected heading directly at us, every space weather agency on the planet will light up simultaneously. There's one more detail that makes this moment different. Earlier this week, NASA published findings from Parker's solar probe. During a 2022 flyby, Parker passed directly through a magnetic reconnection event, the process that powers solar storms. Scientists expected protons and heavy ions to accelerate identically. They didn't. Protons scattered like a flashlight beam. Ions fired in a straight line, like a laser. Why does this matter? Because our ability to predict how hard a storm hits depends on understanding the physics driving it. And this discovery means the models are incomplete. We're getting better at predicting when a storm arrives. We're still learning how hard it hits when it gets here. So here's where we stand. Tonight, enjoy the aurora if you can see it. Check NOAA's Ovation map. It updates every 30 minutes with real-time visibility predictions. But keep watching the sun, because somewhere behind that bright disk, an active region is turning. It exploded 3 times in 3 days. It launched a CME that will reach Mars, and in roughly a week, it faces Earth directly. Maybe it'll be exhausted by then. Maybe the magnetic field will simplify, and it'll cross the Earth-facing disk without incident. But maybe it won't. I'll update the moment that region rotates into view. If it's big and complex, you'll hear about it here. If it's nothing, I'll tell you that too. The sun just reminded us of something we keep forgetting. We live inside the atmosphere of an active star. And right now, that star is doing something we can't fully see, but we can hear it. 3 times in 3 days from the other side. What would you do if NOAA issued a G5 warning with 72 hours of lead time? I want to hear your honest answer, because the sun is going to ask that question again. The only question is whether we'll be ready.